give a warm round of applause for Alban!
Hello. Hi. I'm Alban. I'm going to be talking to you about quantum computing. So I thought I'd start off with a little game of guess my phone password. So if you'd like to play, there's a barcode that will come up on the screen, and that will take you to Kahoot, and you can guess any 6-digit passcode and see if you can get my phone password. Yeah, there it is. Just need to put in a nickname. And yeah, go for it. Yeah, I'll give you like 30 seconds. Oops, a lot of people. All right. Is that everyone in? Is anyone else desperate to play? No? 2 seconds. All right. So we'll start with that, if that's okay. Yeah, let's go with that. Okay, so you just have 30 seconds, guess any 6-digit number as my passcode and see if you can get it. Yeah, there's not much of a game, there's no prize or anything, but... All right. All right, 5 more seconds. 3, 2. Should we get a wee drum roll for the answer? Start with drum roll. Oh. Oh, 2 people got it right. Yeah. Who got it right? Does anyone know? Oh, it was you. You knew the answer. Cheat. All right. Right, there's no prize. Yeah, for the record, that's not actually my phone password, so don't be trying anything. All right. Yeah. So there was actually a million different options, so yeah, 1 in a million chance that you got that right, so well done. Who needs quantum computers? We have this guy. But yeah, we actually have computers nowadays that can solve this problem pretty well. These computers are based on bits, which can either be zeros or ones. So we can use just a large combination of zeros and ones to represent any number. So all a computer would have to do is start from the first option, which would be 0, 0, 0, 0, 0, 0, and then check if that's right. And if it's wrong, it'd go to 0, 0, 0, 0, 0, 1, and check every possible option until it eventually reached my phone password. And as you can imagine, if it had to go through a million different options, it could take some time. But we actually have very powerful supercomputers now that can do this in less than a second, which is pretty impressive. But what if I got you to guess a 12-digit passcode now? There's significantly more options. And the same supercomputer would take 25 seconds to solve that. And if I included letters, it goes up to 3 weeks. If I include uppercase and lowercase letters, it's 100 years. And if I include symbols as well, this same supercomputer would take 34,000 years to solve that, which is a long time. Probably not worthwhile. So I'm here to talk to you about a new type of computer called a quantum computer. And here's a picture of one that we have in our lab in Glasgow Uni. They're pretty big compared to a normal desktop. And yeah, all you need to know, like all this stuff from the top is just a bunch of ugly wires and technology used to keep it very cold. But at the very, very bottom, there's a little chip. And that chip is the quantum computer. And unlike traditional computers, which rely on bits as either zeros or ones, these quantum computers run on these things called qubits, which can also be a 0 or 1, but it can also be in an intermediate state when it's kind of both simultaneously. And this allows it to exist in infinitely more states at the same time. And it's this really unusual property of quantum computers that allow them to explore numerous solutions at the same time. And it makes it much faster at performing tasks like cracking passcodes. What would have taken a supercomputer thousands of years can now potentially be accomplished in a matter of seconds. So these machines are really powerful, and this power can be used for things like simulating molecules to discover new drugs for diseases, or just encrypting data better. It's pretty useful. So how do we make one of these? Well, to begin, we need to choose which quantum system we want to make our qubit from. So we just need to choose some system in physics where we have a 0 state, a 1 state, and these in-between states. So there are many options. Some people look at using the energy gaps in an atom. Some people look at using the polarization of a photon. But I want to talk to you about using the spin of an electron. So spin might sound confusing, but it's potentially a concept that you're already familiar with. Basically, when a charged particle moves, it creates a magnetic field. Like the Earth, for example, has loads of charged metals in it. And when the Earth rotates on its axis, these charged metals move around. And it's this spinning motion that creates the Earth's magnetic field with a north and a south pole. And if you were to imagine if the Earth suddenly started rotating in the opposite direction, then the poles would flip as well. And this is the exact same for electrons. When these tiny charged particles spin really fast, they generate these magnetic fields. And when it spins one way, it creates a magnetic pole in one direction, and this is called spin up. When it spins in the other way, the magnetic poles are flipped, and this is called spin down. And the weird thing is, electrons can kind of exist in a state where they're somehow doing both at the same time. And if you're getting confused at this point, then you probably understand it. But yeah, we can use these as qubits, where a spin up could represent a 0 and a spin down could represent a 1. So to make a proper functioning quantum computer, we just need to be able to control these spins. We need to be able to flip a bit from a 1 to a 0, or from a 0 to a 1, or into these in-between states. And the way we do that is by using these things called microwaves. And although we don't use microwave ovens in our labs, they actually work on the exact same principle. So we can use these to help us understand how to control spins. So first of all, microwaves are just part of the electromagnetic spectrum. Just like visible light, ultraviolet, radio waves, they're all just the same thing. They're just electric fields and magnetic fields together, moving through space, oscillating up and down. So how can we use this to heat up our food? Well, basically, our food has loads of water molecules in it. Water's H2O, so 1 oxygen, 2 hydrogens, and the oxygen is slightly negatively charged, and the hydrogen is slightly positively charged. So if we were to apply an electric field to this that faces down, then this will push the atom so that the water molecule will align with the field orientation. And if the electric field is flipped, then the water will also rotate to follow that. So now when we apply a microwave, which has an electric field that's oscillating up and down, up and down, up and down, this will result in the water also oscillating at the same time, effectively vibrating. And so in our food, when we have loads of vibrating molecules, this generates heat, and that's what heats up your food. And the principle is the exact same for spins. When we apply a microwave to a spin, the spin will follow the magnetic field in that microwave and effectively start vibrating. And we can use this to control their dynamics. And that's what my research looks at. But instead of looking at single spin systems, I look at materials with millions of spins all facing random directions. And by placing them under a strong magnetic field, I can align all these spins in one direction and effectively study how their behavior as a collective is affected by microwaves. So this is what a typical data set looks like for me after I've shot some microwaves at spins. And I know this is probably meaningless to you, but all you need to know is that there are 2 branches in greenish. And the position of these branches gives us information about how the microwaves interact with the spins. And this interaction will change a lot based on the properties of the microwave, like its shape, its size, its frequency. And so my supervisor, he's crazy. He thought it'd be a good idea to check every single microwave condition and see how it affected these branches. So I did that. And it took a really long time. And then, to make sure that it was correct, he made me do it again. And to be honest, there was no reason for me to share that with you today. I just wanted to show you the pain I went through to get these results. So yeah, anyway, thankfully this was not all in vain, because in the end we managed to use all these plots to determine robust ways to control these spin systems with microwaves. And I believe the knowledge that we gain from this will help us understand how to control spin-based qubits and other quantum technologies in the future. Thanks for listening.